this lecture of the linear partial differential equations. Today again I will solve the problem based on the Lagrange method, and I will try to solve these 4 problems with the help of the Lagrange method. And these 4 questions are different from the questions which I have already given you in the last lectures. So let us solve question number 1. The Lagrange auxiliary equation is dx upon y plus z equal to dy upon z plus x and then equal to dz upon x plus y. Now all these 4 questions are of different type. In this type we will use the rule of proportion. Now let us minus these 2 terms. So this will be your, let us consider dx minus dy. Now your dx minus dy will be, here you can see that this will be your, now this dx minus dy will be y minus x, and then consider dy minus dz, and now your dy minus dz will be, now this x will be cancelled, so we will get z minus y, and then dz minus dx is equal to, this y will be cancelled and we will get x minus z. So now let us assume this one as term 1 and this one as 2 and this one as third. So take 1 and 2. Taking first term and second term, we will get d of x minus y. We can write it as d of x minus y and take minus sign common. So we will get d of y minus z and take minus sign common, then we will get y minus z. Now this minus is cancelled, so on integration we will get log. Now this will be your, if you assume x minus y as t, then this is your dt upon t. So dt upon t means log t. So this is your log x minus y, and here we will get log y minus z plus some constant of integration log c1. So your first answer will be log a minus log b. So this will be your log a upon b equal to log c1. So your first answer is, this give you your first answer, which is your x minus y. This implies that x minus y upon y minus z equal to c1. This is your first answer. Then now let us take second term and third term. Now taking second and third term, we get d of y minus z divided by y minus z equal to d of x minus z upon x minus z, and so now here we will have to take minus sign common, so we get minus of this. I think this has to be your z minus x. Let me check, let me cross check the problem. This was your d of, this was your z minus y, I think z minus y, and here x minus z. So dy minus dz upon z minus y equal to dz minus dx upon x minus z. Okay, it is correct. So now on integration we get log with negative sign equal to log x minus z plus some constant of integration log c2. So you can write it as minus log of c2. So this constant will come here, and in the right hand side we will have log x minus z into y minus z. Now this is your log a plus log b, so this will be log x minus z into y minus z. And the left hand side we have log c2, so your constant number 2 will be x minus z into y minus z. So that means our solution is, therefore solution is f of, the first solution was, I think the first solution was our, this was I think y minus z upon z minus x, and the second solution is x minus z into y minus z. So this will be your answer, f of u comma b equal to 0. So please cross check the value of C1. If this is the value of C1, then your answer will be f of y minus z upon z minus x in comma this equal to 0. So this is the solution of the first part. Now let us solve the second part. Please cross check your solution. In the second part, we have y square. So auxiliary equation will be your dx upon y square x minus y equal to dy upon x square y minus x equal to dz upon z into x square plus y square. And let us take first and second term. Clearly you can see that from first and second we will get one answer. So on taking first and second, we will get dx upon y square equal to, now this x minus y and y minus x will be constant or cancel, and we will get this. So on cross multiplication we will have this term equal to 0. So on integration, our first solution is, on integration we will get x cube upon 3 plus y cube upon 3 equal to some constant, say c1 upon 3. So your first solution is x cube plus y cube equal to c1. So this is our first solution. Now to find second solution, let us subtract first and second. Now let us find the another solution. So now each term will be equal to, each term is equal to, now dx minus dy will be, now this dx minus dy will be, so here if you take minus sign common, then this will become your plus, so we'll get x square plus y square, and then this minus this, so this will become plus sign if we take minus sign common, so we'll have x minus y, and this is equal to the fourth term, because you know that in proportion all the ratios are equal to each other. So here you can see that dx minus dy upon x minus y is equal to dz upon z. So you can write it as d of x minus y upon x minus y equal to dz upon z. So on integration we will get log x minus y equal to log z plus some constant log c2. So your answer is x minus y upon z equal to c2. So this is your second solution, and thus the general solution is f. Thus our general solution is f of the first solution. Your first solution was, I think, x cube plus z cube. The first solution, let us see the question. The first solution was, yes, x cube plus y cube. This was your first solution, and the second solution is x minus y upon z equal to 0. So this is your general solution of the problem number 2. Now let us solve problem number 3. So in problem number 3 we have auxiliary equation as dx upon x square minus y square minus z square, then it is equal to dy upon 2xy, then equal to dz upon 2xz. So from second and third we will get one answer. So from second and 3, from second and 3 we will get dy upon y is equal to dz upon z. So on integration we get log y equal to log z plus some constant of integration. So we will get log y upon z equal to log c2. So your first solution is y upon z equal to c2. Sorry, say c1. So we have one solution, which is your y upon z equal to c1. So this is your first solution. Now to find second solution, now we have to get the second solution for the third part. So for that, now each term is equal to this was your dy and this was your z. Now your each term will be equal to, okay, now choose your multiplier. Suppose that we multiply first term by x, then second term by y, and then third term by z. Let us see what happened. Now here you will see that in the first term we will get x cube, then we will get minus xy square minus xz square. Then as we are multiplying this term by y, so this will be your 2xy square. And the third term will be your 2xz square. So now each term is equal to this term. Now this is equal to x dx plus y dy plus z dz divided by, now this is your x cube plus xy square plus xz square. So this is, if you take common x, then you will get x square plus y square and plus z square. Now each of these three terms are equal to this term. Each of these three terms is equal to this term. So we can take this term equal to any term. So thus, let us take the third term. My third term, I think my third term was dz upon 2xz. So let us take this third term equal to this term, because in proportion all the three terms are equal to this term. So we have this thing. Now this x and x is cancelled. So on integration, so we can write it as dz upon 2z is equal to, and here we can take this 2 here, so we will get here as 2 times x dx plus 2 times y dy plus 2 times z dz upon x square plus y square plus z square. Now if you take this term x square plus y square plus z square as t, then we will get 2x dx plus 2y dy plus 2z dz as dt. So if you take this term as t, then the numerator will be dt. So on integration we will get, on integration we will get log z equal to some log t, and t means this term plus some constant of integration, say log c2. So your answer will be z upon x square plus y square plus z square equal to second constant, say c2. So this is your second solution. Thus our general solution is, f of y upon z. This was your first solution, and the second solution is z upon x square plus y square plus z square is equal to 0. Here we can take the constant as 1 by c2. If you take constant as 1 by c2, then our c2 will be x square plus y square plus z square upon z. So we can interchange this numerator and denominator. So that will be your another solution. Now let us solve the fourth part. In the fourth part, our auxiliary equation is dx upon x square minus yz, dy upon y square minus zx, and then dz upon z square minus xy. So we can also write it as dx minus dy upon, now this will be your x square minus y square minus yz plus zx equal to dy minus dz upon, this will be y square minus z square, then minus zx plus xy, and say dz minus dx, and this will be your z square minus x square, then we will have minus yz, dz minus dx, that means z square minus xy, then we will have minus xy plus yz. Now we can also write them as dx minus dy. Now here if you take x minus y common, then we will get, from here we will have two factors, one will be x plus y and another will be x minus y, and from here if you take z common, then we will get x minus y. So in the bracket we will have x plus y plus z, and here this is your dy minus dz upon this is your y minus z. So y minus z is common, so in the bracket we will have y plus z, and then from here we will get x. So in the bracket we will have x plus y plus z. Now at this place we will have dz minus dx, then this will be your z minus x. Now in the bracket we will have z plus x, then if you take common y here, then we will get y. So now you can see that in all these three terms our x plus y plus z is cancelled. So we have, therefore, d of x minus y divided by x minus y equal to d of y minus z upon y minus z equal to d of z minus x upon z minus x. See, this is your first and this is your second term and that is your third term. Now first and second term will give you log x minus y equal to log y minus z plus some constant of integration, say log c1. So from here we will get x minus y upon y minus z equal to c1. And similarly if we take second and third implies d of y minus z upon d of y minus z equal to d of z minus x upon z minus x. So from here we will get log y minus z equal to log z minus x plus some constant of integration, say log c2. So from here we will have y minus z upon z minus x equal to constant of integration c2. So thus our solution is, thus we have solved all the 4 questions. Therefore our solution is f of the first solution x minus y upon y minus z, y minus z upon z minus x. So this is your answer. We can also write it as, the solution as x minus y upon y minus z equal to some function of y minus z upon z minus x. This is the another way of writing. So this is our solution. Now let us one more question on integral surface. So question is, find the integral surface of the PDE, and the partial differential equation is xy square plus zp, then minus y x square minus y x square plus zq equal to x square plus y square. Let us find the integral surface of this partial differential equation, which contains the straight line x plus y equal to 0 and z equal to 1. So solution. First of all, let us find out its general solution. And for the general solution, our Lagrange auxiliary equation is dx upon x y square plus z equal to dy upon minus y x square plus z, and then dz equal to dz upon x square plus y square. So this is your Lagrange auxiliary equation. Now let us take multiplier 1 by x, 1 by y and 1. So now you can see that all of these three terms will be equal to, let us take dx upon x and here dy upon y and here dz. Then in the denominator we will have, now if you have taken dx upon x in the numerator, then in the denominator we will have y square plus z, and here we will have minus x square minus z, and at here we will have x square plus y square. So you can see that my x square is cancelled, z is cancelled, but this y square remains left. So I think this multiplier will not work, so we will have to change our multiplier. So we have to, now this multiplier is not working, so now you can see that here we are having y square plus z, then minus x square minus z, and here we have x square plus y square. If we take minus y square minus z and here plus, then again it will not work, so this multiplier is not working. So now let us multiply this first term by x and say the second by y. This is your hit and trial method. If the multiplier works, then it is good, otherwise you have to assume another one. So multiply the third term by z. Now let us see what happens. So the first term will be your x square y square plus x square z. Now the second term will be minus y square x square minus y square z. Now the third term will be zx square plus zy square. Again you can see that this x square y square is cancelled. From here our x square y square is cancelled and y square z is cancelled. So again it is not equal to 0. So if it is not equal to 0, then now we have one more choice. If you take the multiplier as dx upon x plus dy upon y, then dz upon z, then let us see. I think there is some mistake in the problem. Here we have a z. The right hand side is, I think, wrong. Here we have x square minus y square into z. So there is a mistake. Here we have x square minus y square into z. Now our old multiplier will work. So now here we will have dx upon x, then we will have dy upon y, and then we have dz upon z. Now in the denominator we will have y square plus z. Now this will be minus x square minus z, and here we will have x square minus y square. So now you can see that your denominator is 0 because this y square will be cancelled with this one, x square is cancelled and z is cancelled. So that means this part is 0. So this will give you dx upon x plus dy upon y plus dz upon z equal to 0. So on integration, dx upon x will be log x, dy upon y will be log y, and then log z equal to log c. So this will be your log a b into c equal to log c1. So your constant is c1. So your first solution is x y z equal to c1, which is your constant of integration. So we have one solution. Now let us find out the another solution. Okay, this was your dx upon this one, and here we have dy upon this one, and then we have dz upon this one. Now each term is equal to, now let us take multiplier as x, then as y, and then as z. Let us see what happens. So now if you take x here, then we will get x square y square plus x square z square, and here we will get y square minus x square and minus y square into z square. Then in the third term we will have x square z square minus y square z square. Now this x square y square is now this term is not 0. So if you take minus z here, then we will have to take one minus sign here. Now I have taken multiplier as x, and at here I have taken multiplier as y, and here I am taking multiplier as minus z. So this will be your plus x dx. Here we will have y dy, and here we will have minus z dz. So in the denominator we have x square y square plus x square z square. And as we have taken multiplier y, so this will be your minus y square x square minus y square z square. And here we have taken the multiplier as minus z, so this will be your minus z square x square and plus z square y square. Now you can see that your denominator is 0. This will be cancelled with this one. X square z square is cancelled and y square z square is cancelled. So again your denominator term is 0. So this is your 0. Now on cross multiplication, because all these three terms are equal to this term, so we will have x dx plus y dy minus z dz equal to 0. So on integration, we get x square upon 2 plus y square upon 2 minus z square upon 2 equal to some constant of integration, say c. So this is your x square plus y square minus z square equal to 2 times c. Let us assume 2 times c as constant c2. So this is your solution. Therefore our general solution will be, general solution is phi of the first solution, comma the second solution. Now here we have to find out the integral surface. For integral surface, we will have to remove the constants of integration. So let us take the parametric coordinates. Let x equal to t, and then as we have the straight line x plus y equal to 0, and this is given in your problem, so our y will be minus t, and also we have given z equal to 1. Thus, therefore x is t, y is minus t, and z equal to 1. Now put these values in c1 and c2. So therefore your c1 will be x into y into z. So this will be your x, that means t, y is minus t, and z is 1. So this will be your minus t square. So that means your c1 equal to minus t square, or you can say your t square equal to minus c1. Also x square plus y square minus z square equal to c2. So as x is t and y is minus t, so this will be your t square plus t square, and z is 1. So this is equal to c2. Therefore c2 is equal to 2t square minus 1. Now as t square is minus c1, so this will be your minus 2c1 minus 1. So you can say that 2c1 plus c2 plus 1 equal to 0. So we have a relationship between c1 and c2. Therefore our solution is, our integral surface is now 2 times c1, that means 2xyz, plus c2, this was your c2, x square plus y square minus z square, and plus 1 equal to 0. So this is your answer. So this is the solution of the problem. Now let us solve one more problem. Find the equation of the integral surface. Find the equation of integral surface of the PD, and the partial differential equation is 2 times y z minus 3 p, then we have plus 2x minus z cube equal to y 2x minus 3. which passes through the circle z equal to 0 and x square plus y square equal to 2x, which passes through the circle z equal to 0 and x square plus y square equal to 2x. So let us find out its solution. Solution: Lagrange auxiliary equation is dx upon 2y z minus 3 equal to dy upon 2x minus z and dz upon y 2x minus 3. Now let us take first and third term, because you can see that in first and third our y will be cancelled. By 1 and 3 we will have dx upon 2 z minus 3 is equal to dz upon 2x minus 3. So from here we will get 2x minus 3 dx is equal to 2 times z minus 3 dz. So on integration, this will be your 2x minus 3 whole square upon, now as we are integrating with respect to x, so this coefficient of x will come in the denominator, so this will be a 4, and in the right hand side we will have, or if you do not want to take it as a single term, then the integration of 2x will be your x square upon 2, so this 2 will be cancelled. Then we will have minus 3x. Now here this will be your z square by 2, so this 2 will be cancelled, and here we will have minus 6z. So this is your minus z square plus 6z equal to, say, constant c1. So this is your first solution. So x square minus 3x minus z square minus plus 6z, and if you take it on the left hand side, then this will be your minus 6z. So this is your first solution. Now for the second solution, let us take the multiplier as, now each term is equal to so if you take multiplier as dx upon 2, then we will have dx upon 2 and say plus dy. Now this will be a yz, and if you multiply this by y, then let us take multiplier here y, and in the third term as z. That means we have taken the multiplier as 1 by 2 comma y comma 1. Let us see what will happen. So here you can see that now from each term we have y common. We have already taken this 2 common here. So here we will have z minus 3. Now at this place we will have 2x minus z, and here we will have 2x minus 3. So that means to cancel this term, let us take multiplier as minus z. Now this will become your minus 2x, and here we will have minus plus 3. Now you can see that your z is cancelled, 2x is cancelled, and 3 is cancelled. So that means on taking the multiplier as 1 by 2 comma y comma minus 1, our denominator is 0. So if this is 0, now and as each of these terms are equal to this term, so on cross multiplication, we have dx upon 2 plus y dy minus dz equal to 0. So on integration we will get x upon 2 plus y square upon 2 minus z equal to, say, constant c, or you can say x plus y square minus 2z equal to some another constant c2. Now to find the integral surface, let us assume we have given the equation of circle as z equal to 0 and x square plus y square equal to 2x. So let x equal to t. Now if x is equal to t, then your y will be y square will be 2t minus t square. So now let us put these values in equation number in C1 and C2. Therefore our C1 will be, from here our C1 will be t square minus 3t. Our z is 0, so these two terms will be 0, so this is your C1. So we have this value of C1. Now from here also our C2 will be x square plus y square minus 2z, and this is equal to, now x is t, so this is your t, y square is 2t minus t square, and z is 0, so that will be your 0. So this is equal to 2t minus t square. Now thus you can see that C1 plus C2 will be your 0, because if you add these two terms, therefore if you add C1 and C2, then you will see that their sum is 0. So we have C1 plus C2 equal to 0. Now let us put the value of C1 and C2. So C1 was, I think your C1 was, I have deleted this C1. So our C1 was x square minus 3x, and then I think there was z square and plus 6z. This was your C1, and C2 is this one, x plus y square minus 2z equal to 0. So this is your answer. Or you can say x square minus 2x minus z square plus 4z equal to 0. So this is the equation of the integral surface. Please let me confirm the solution. This is your x square and there is one y square. So we have the solution as x square plus y square minus z square minus 2x plus 4z equal to 0. So this is our solution.